Welcome to this training about machine learning, models, Splunk, machine learning toolkit. We're going to cover a lot of different things during this training. And I'm going to go right out. I'm going to be apologetic, but I'm not going to be apologetic. I'm intentionally going to be a little controversial in the things I'm saying, mostly because I want to open your eyes to be thinking of things a little differently. I have done a lot of research. I spent a lot of time doing this, and I'm starting to see that there's a lot of different narratives that go on when it comes to machine learning. So I'm going to be a little controversial in the things I say, solely just to get you to think a little bit outside of the way things are shown. And there's a way of thinking that machine learning goes, and I want to open up other ways, other dialogues about machine learning. Anyway, the first little bit of this presentation will be mostly theoretical, a lot of slide presentation, and if this is kind of boring, you're not really interested in it, by all means jump down. I'll have references down below where you can bookmark, where you can get moved forward in the video and not have to watch all this, and we'll go into the live demos and stuff we want to talk about. But anyway, let's get going into machine learning. We're basically going to look, as it says here, a systematic approach to using Splunk programming language, machine learning toolkit to gain quick wins and insight into your logs, to help supplement, to help bring about a different way of doing machine learning than is traditional. And the first thing you got to do is, what is a model? If we're going to talk about machine learning, we need to define a model. And I found this definition, I kind of liked it. Machine learning model is an expression of an algorithm that combs through mountains of data to find patterns or make predictions. And then it's fueled by data. Machine learning models are mathematical engines of artificial intelligence. But what I really like is this statement here. It combs through mountains of data to find patterns or make predictions. Anything that can comb through mountains of data to find patterns or make predictions is theoretically, by this definition, a model. And so machine learning, I want you to expand your mind on what could be a machine learning model. Basically, it's fueled by data. You bring in data, and model uses mathematical engines to create a form of intelligence, this artificial intelligence. So I want to place that premise down, and when I find that model, you'll understand why I'm going to say the things I say later on about the different models in machine learning. First off, let's talk. As a general rule, I have found it's really easy to, there are thousands of models out there. And the basic concept is it's math. There's lots of different mathematical models of ways to lump, cluster, predict data, but they all generally fall into a category. And I'm just going to use that so you can kind of, I have found when I've talked to people about machine learning that I want to talk to them, I just want to say, hey, what is it that you're looking for? What kind of model is it? And so is it a regression model? Is it classification? Is it forecasting? Is it clustering, or is it anomaly detection? And these first three here, they're kind of predictive. We're going to discuss each one of these, and I'm going to give a definition to them. Clustering is grouping similar types of data together, and anomaly detection, finding outliers in your data. And if you use those kind of categories, then you can break it down and say, all right, so the model fits in this overall parent, this overall category, and then we can talk about the actual model. And it helps make sure that we're actually trying to solve the problem with the right type of tools. And so regression, the basic concept here, regression models or predicts a number from a variety of bunch of contributing factors. As I use here, this example, we might have CPU percentage, amount of disk reads and writes, and you're going to use a regression model to predict the amount of power that a machine is likely to draw both now and in the future. Basically, you've got a bunch of data points, and you're going to make some form of prediction as down the road as to what, if I have this much CPU and this much disk writes, this is the amount of power I'm going to use, etc. And so there's a regression line. How closely do your data points fit that line? That's kind of the basis of regression. Classification, this is you're predicting a category or class from a number of contributing factors. It's again predictive analytics. I'm going to give an example here, which is basically from the Splunk themselves. They say, hey, we've data on a user behavior on a website or within a software product, and using this, you predict whether the customer is going to do what the customer is going to do based off certain behaviors. I would go a different matter. You could do contributing factors if you're doing network analysis. If I see a machine responding on these ports, that might make it this type of machine. If it's listening on port 80 traffic, I can categorize it as a web server. And so those are contributing factors, and you're classifying. You're classifying what a category of a system based off different data points. If it's got a beak, it's got feathers, it's got wings, it's probably a bird. That's the concept of classification. Forecasting. This is another predictive model, but typically you're looking for a single value. And I like this one like profit per day or CPU usage per minute. And what you do is you have a whole bunch of, over time, the amount of profit you've made or the amount of CPU, and that you're going to predict that. And you can say, you know what, I think that based off the results of the sales we've had the last 5 years, we're going to make this much this quarter. And because we keep making more money each quarter, we make this much, we can expect to see this much growth. Or we could see that we're going to use this much CPU. The concept is you're going to, based off previous numbers, you predict future values. That's forecasting. Clustering. This is very similar to the classification model, but in this case, all you're really trying to do is you're trying to cluster. This is actually more the bird. Sorry, the clustering, grouping similar groups of data points together. Um, you might want to group customers together based off their buying behaviors, how much they spend, or many items. Cluster monitoring group together the features you specify. It kind of to me, I look at it as taking it a little bit further. Now you're going to take actions based off the categories that you've created, the groups that you've created, whereas the classification makes a class. Here, you're kind of grouping behavioral based. You're still a customer, but you're going to be a high spending customer, low spending customer, what kind of behaviors and what makes that. They're very similar. This is not a machine learning. I don't want to get too much, but just kind of get that principle. It's another way of lumping things together, categorizing. And the last one, anomaly detection. This is finding outliers in your data. Um, you're going to compute an You're going to try to compute an expectation based off different learning types. You might comparing with reality and trigger an alert when the discrepancies are too great. So, for example, very simple: find new traffic on a protocol. You look at this protocol, you see how it's been behaving, you see that there's IP tuples, IPX talks to IPY. All of a sudden, there's a new communication. That's an anomaly. You look through your logs and you look for things that rarely occur. You could see we are very used. This should be the bread and butter for a cyber person because they're very used to this is how things work. If I tell you what port does SSH traffic occur on, almost everyone's going to say port 22. There are exceptions, and those are the anomalies. We want to identify it. Anytime you see someone using abnormal ports, typically that's not a normal user. It doesn't mean it's bad, but it's abnormal. And so if someone's all of a sudden using a different high port, maybe they're trying to encrypt their traffic and send it out. Or what if they're using port 22, but it's not SSH traffic? Maybe that would be an anomaly, and there'd be reasons they're trying to do that, but you're looking for anomalies. That's just by our nature, cybersecurity analysts look for anomalies. That's one of our main things we do. So where do we start? This is really a cyber analyst discussion on machine learning. And so if you're a cyber analyst, you might see the following. IDS alerts. If I get IDS alerts, that's a classification. I see this port, I see these set of bytes. I'm going to call it an alert. That's almost like a classification model. It's oversimplifying it, but I'm just trying to get you. That's how you can kind of think of it. Fingerprinting a system or deriving its OS and its purpose. That would be classification or clustering. Determining if an alert is a false positive or legit. Even that solving these alerts is technically kind of anomaly detection. You're looking at it and you say, you know what? I see this alert and it fires off every day. Same machine fires it off. It's not an anomaly. It's regularly occurring. Even though it's an alert, I know it happens all the time. I'm going for it. Typically, I know a lot of analysts, when they get a whole bunch of tickets and there's I got 15 of this IDS alert, 12 of this alert, and I get one of this. Typically, they want to look at that one. They want to see that rare item, the the alert that hardly ever fires. I don't want to see the alert that fires all the time because it's probably not an anomaly. The one that fires once, that's an anomaly. So this is stuff we do on an everyday basis as analysts, looking for overall bad. When you were just digging through the logs and you're looking at behaviors, you know what is normal, and you're looking for what's not normal. But you can't know bad if you don't know the good. I can't give you, you have to be exposed to this kind of stuff, and that's what we do as analysts. We've seen what's normal over and over again, and all of a sudden you see something that's not normal. You go, oh, that's interesting. That's your brain automatically doing anomaly detection. Most free flow analysis mostly comes down to determining if it seems legit or if it's abnormal. I mean, that's what we do. We look at the stuff, we gather the facts, and we say, based off what I'm seeing, I'm calling this abnormal. I'm saying it's not. I'm closing the ticket. I'm furthering the investigation. Every day, as cyber analysts, we are doing anomaly detection. So I'm going to really focus on anomaly detection because that's something that should be very familiar and near and dear to your hearts. And okay, so what do we do? We've talked about machine learning. We've kind of talked about how we categorize the stuff, the different umbrellas, the different categories it fits in, the umbrellas. Now, the most important thing, and I find that often it's neglected. When I ask, what is this model? What is it doing? A good model, to me, this is my opinion, a good model has a good story. They can say, I am looking for this, this, and this, and that's what I'm trying to do. I'm trying to identify birds. And what I'm trying to do, how I'm trying to identify birds is I'm taking a whole bunch of body parts and I'm putting together, and if they have the right body parts, it's a bird. I mean, that makes sense to me. You want a story, it needs to make sense. If you say, I'm looking for bad, I really don't know what you're doing. I get it. I understand from a high level. And as cyber analysts, we say it all the time. What are you looking for? I'm looking for the bad stuff. What you really need to go down to is I'm looking for a golden ticket attack. I'm looking for brute forcing. I'm looking for the file hashes moving around. I'm looking for weird processes going off. That is a little closer to the story we want. And even those might be too generic, but it's a lot better than just saying, I'm looking for bad. I'm looking across the entire spectrum and I'm trying to say what is good and bad on the network. That's a lofty goal. It's going to be very hard to measure. It's going to be hard to create. I want to stay, let's get really good stories. When it's possible, get a good story that's very easy to understand. And I hope as I give use cases at the end, I have established a good story and you'll see it. I love this quote from Alice in Wonderland. Would you tell me, please, which way ought I to go from here? The Cheshire Cat responds, that depends a good deal on where you want to go. Alice says, I don't care much. And the Cheshire Cat responds that it doesn't matter which way you go. If you don't know where you want to go, any path can lead you there. But again, I don't recommend this path for beginners. I think you'll be much more successful if you have a good story, a good narrative, and you know what you're looking for. It makes the rest of the stuff we're going to talk about much easier to accomplish. So let's establish a good story when we're building machine learning models. I like this workflow process. I've seen it used in many different ways. They use different terminology, but the general concept is it's cyclical. And it's never always perfect. It's not like this becomes first step, second step, third step, fourth step. They can intermingle, but as a general rule, we need to collect data. You can't do anything. The very concept of model of machine learning is that you're going to look through data to make decisions. Well, if you don't have data, you can't do it. So thereby, the first step has to be collect data. Next, we got to clean and transform that data. We have to clean and transform because not all the data, machine learning models, general rule, they want statistical information. They're statistical models. And I'm going to keep throwing that out there because that's a caveat that's going to make people upset as I go later on and talk about machine learning is statistics. But they are statistical models. They take statistical values. You walk like a duck, you talk like a duck, you are a duck. You're probably not a platypus. Um, The point is you need to clean and transform your data into numeric uh, statistical values. IP addresses, for example, they're not really great in machine learning because they're strings. And so you've got to find a way to obfuscate, change them into integers. I am going to point this a little out because I'm just going to poke a little problem. Be careful, though, as you give them numerical values, all of a sudden they become statistical values inside your model, and they themselves hold statistical relevance if you're not careful when you build your model. An IP address is really a category. It's a classification, it's a data point, but make sure when you clean and transform your data, it doesn't actually weigh into the model. For example, 1.1.1.1 address is probably not supposed to weigh more than 1.1.1.2. Does that, I hope that makes sense. We will definitely cover that, but we don't want to give statistical value to these numbers. And the biggest problem is you convert them to numbers, all of a sudden is one more important than two. Let's say IP address one X becomes a one, IP address Y becomes a two. Did you end up giving more value to it? I spent way too much time on this, but I just want to be careful. Cleaning and transforming the data, that is a task in of itself. A lot of that, a lot of your time in machine learning is actually going to be spent in these two steps: collecting the data and then cleaning and transforming it so that you can then explore, visualize, and build your models. But once you've got your data and it's clean and transformed, you'll explore, you'll visualize, you'll find the key data points, you'll then attempt models on it, you'll evaluate the effectiveness of the models, you might come back, explore, and visualize some more, clean and transform the data, use different models, evaluate. Often I will run multiple models and I'll just see which one I like better because I'll have a test data and I know this reflects what I think is reality. This is my reality. I joke. Hopefully we know what reality is, but sometimes it is. It's your perspective of reality, and I want a model that matches closest to my reality. And so I can put 3, 4 different models and run the same data through it, and I see which model closest reflects what I think is truth. Anyway, I evaluate, and then when I'm happy with it, I deploy. Now, deployment is never, you're never done. As you go through, you need to keep retraining the model. You'll learn more information, environments change. You got to keep that model retuning, and you keep going through that process. But this is the general workflow process. I spent a lot of time on clean and transform. I shouldn't have done that, but what's done is done. We're now going to cover each of these areas a little bit more in detail, so we're going to go back. When I talk about collecting data, if you don't have the data, you can't make the model. It's nice to have a use case story, but if you don't have the ability to get the data, you still won't be able to do anything. I've heard the concept, wouldn't it be really cool if you could get the handshakes between VPN logs and then get all the packets that are going back and forth and see what's going in and going out? That's cool, but if your VPN logs don't have that, you're never going to be able to make a model off of that. You got to have the logs. You got to have that in order to do it. And so collect data is very important. Nice thing is we don't have to worry too much about collecting data other than does the data help us make our models, but we have lots of data because Splunk is just that. It's a tool for collecting data. And so we leverage Splunk, we collect that data, and the data is all sitting in a nice repo if you choose to use the Splunk tools. You don't even have to pull it out. You can just query the data. Next step, explore the data. Once it's ingested, you got to explore it to make sure it's suitable and ready to be used. Is it numerical? Does it work? Sometimes you want to exclude things. For example, if I'm looking at um, anomaly detection and I want to do anomalous login behavior, maybe I'm really focusing on brute forcing or a bunch of failed passwords. I'm not really concerned about successful passwords. There may be a case where you care about both. I'm just using, let's say my model is about finding malicious type scanning, the concept that somebody might have stolen passwords. And in that situation, you would want to know you might set your data to restrict it down the data set and only take logs where the password authentication failed. Or maybe your model is about detecting people who might be impersonating another individual. If they're impersonating and failing on the password, maybe that's not important. And so then you might change it and you only care about authentication that was successful. I've oversimplified it, but I just want to give that point that there's a lot of data points that you may actually not need. And the less data points there are on your model, the faster your model will compute, the easier it is to explain the results of your model. And I will say that analysts will be a lot, it'll be a lot easier to understand. So you'll gain a lot of performance by removing data points that don't make any sense. Don't remove them just to remove them, but at the same time, don't just put a field in there just because it exists. That field should make sense. And restrict down the data as much as possible when that data is irrelevant to the decision-making process. That's my take. Um, anyway, again, it may be controversial, but I have found that that works for me, and I get a lot better results if I can eliminate and not use it a giant pool. I want to restrict down and look at more focused stuff. Data you thing you can also do, you can ingest your data into MLTK so you can easily visualize your data. Um, Depending on the tools you use, if you've ever used, I've watched people and they've used Zeek logs and they're going through the Zeek logs. If you're looking through it through a text editor, that can be a little bit painful. Nice thing about Splunk, it puts it all in a nice graphical format. It's really easy to look at that data. And so I'm a big fan of using Splunk and using some of their capabilities to better explore your data. Uh, Other things, Splunk Platform and MLTK offer several methods that you can clean and transform your data to address many of these issues. I'm going to show, I've kept talking about, you got a lot of categorical values into numeric values. The more categorical values you create that are non-numeric, you get into some serious computing issues going on. It, Splunk just, machine learning models, these mathematical formulas, they're math. Math doesn't really work on strings. Again, I'm just going to say it. These are statistical mathematical models. Thereby, math works on numbers. And thereby, the more you can get your stuff into numbers, the better your models are going to work. And some of your models just won't work if you don't supply them numbers. Splunk has capabilities built in to help you convert some of that stuff. So there's another benefit there. We're going to experiment. Data experimentation is where we start processing and training our data. We look at it, we say, hey, there's a bunch of things to look for anomalies, algorithms, to just kind of experiment and see how that data is working. Did I grab the right data? Is this going to be able to help me be able to train some other models? And so you do some experimentation there. And then ultimately, you're evaluating those results. First, did I experiment with your data? Make sure you're getting useful information from it. When you start with that very first bits of experiments, can you make are you getting useful information? And if you as the person building that model cannot make useful model, if you cannot explain in human language very simply to someone else what your data is producing, you might want to go back and reevaluate your model. It needs to be able to answer and provide useful information. And you have to remember your audience. It's great. We don't, Mathematical results are great. I joke. Um, Outside of arithmetic, my math, I'm not a big fan of. I understand arithmetic. You talk about adding, subtracting, dividing, I get that. But you start using things like, well, this is you start using calculus terms, derivatives, things like that. I'm not 100% sure what you're talking about. You got to bring it down to my language and help me understand it. The results have got to be useful. Are they? And they may or may not. One of the other things you might do, am I even asking the right question from your data? You might be creating a model and it's not even queer, it's not even making the right question. Again, that comes back to frame your question, create a story. You have a good story, frame it. Do you have enough data? Is it sufficient cleaned? Again, you're just looking at this. How's the experiment working? Do I need to do some different things? Then there's some machine learning toolkit model assistance. If you're new to this kind of thing and you're not familiar with how to start to look and evaluate your results, you can use some of these assistants. I'll demo that later in the video, how to use that, but it'll help you quickly assess, did I, is, are these experiments going to show some value? Am I going to be able to do something? And then you're going to be able to, you want to modify and change the range, the thresholds, some scoring metrics on how your machine learning model is going to move forward in the future. And so there's all sorts of toggleable, I don't know, modifiable values in these mathematical formulas. You're going to tweak different values and you'll get different results based off that. And so you're going to play around with those. Then you're going to just tune and iterate. And so basically, you're gonna keep playing with that model, and you're gonna try to make sure how close I got my training data, and this is the expected results. Then I'm gonna put some other data in. Did it give me those values like I expected? One of the things you can do is, if you know, the beauty is if you have some trained data, and then you have some extra trained data that you don't use to make your model, you can put that data in and see how well it match data it's never seen before. If it's not matching very well, go back and tune and iterate. You want high percentage of alerts, of value. The thing is, analysts, remember, these are going to be going to cyber analysts as a general rule. They have a lot of things. They can't just go hunt every little thing that pops up. So the thing has to be, coming back to here, it's got to be useful, it's got to be understandable, and you don't want to be creating a bunch of noise. They don't have time to hunt down a bunch of noise. So you got to make sure these models have high level of confidence. I hear people, well, it's got a 50% confidence level. In other words, I could flip a coin and get the same results. You did a lot of effort. You got to get better than that. You got to get high percentages. And I know I'm sounding really bad, but if you're making, if you're not even 90% accurate, I personally don't want to talk to you at the moment. I'll help you work on your model, but I don't want to have my work and my day-to-day work tied to a model that is fit one out of every 10 logs that come out of it what is completely wrong. I don't want that. And that's, some people, 90% sounds really, really good, but that's a lot of time wasted every time if 10% of the things I'm looking at are invalid. I have to use my time wisely. There's never enough time to look at all the things that are going on in a computer system. You can't be bogged down with a bunch of false information. And so you really need a high level. And so this tuning and iterating is really important. Again, there's lots of assistance, lots of things. Just keep evaluating, reevaluating, training that model. So we all know you don't want your model being 100% because there's problems with that. But I will tell you that as a general rule, when you're anomaly detection, the closer you get to 100%, I don't want to say that 100% is the goal that you're going for, but I will say the closer you can get there is actually the ideal. Don't let that concept that you've got your model trained so much that you're missing the other things. There's some truth to that, but in the cyber world, we it you're gonna miss you're it's too anomalous to begin with. So don't make things worse by providing data that's not valid. Um, so anyway, it's a balancing act. I'm not gonna, there's no silver bullet. There's no perfect numbers to say there. Just try to make your model be as accurate as possible and keep tuning it till you get there. All right, then you're going to deploy that model. You're going to apply it on new, never seen before data, see how it works. You definitely want to keep checking your model outcomes and make sure that they are still getting data as seen. I love the idea of putting them in red team, blue team exercises, and you want to put your model out there and you want to make sure, especially in something so blatant as a red team, where somebody is not trying to be really covert. You definitely want to make sure that your model is detecting the actions of that red team pen tester. Um, that is, if your model can't detect a red teamer, you really want to go back to that model and say, all right, let's reevaluate how we're doing. Um, it's the really advanced persistent threats. They're a lot slower. They're a lot more. They're going to take their time. They're going to be a lot quieter. They're going to be making sure they don't trigger any gates. Red teamers, they don't have much time. They got to get into and out of that system in a day or two, and so they're going to be triggering everything they can. They're going to try not to trigger every alarm, but they're going to be making so much noise. Your model better detect them. I joke, if you're only catching 50% of the bad that your model should have caught with a model on a red team, you definitely want to go back and reevaluate it. That is, to me, it's good, but it's nowhere uh, ready for primetime production. It's got to be much better. Anyway, so in the MLTK, you got assistance. You helps you. The beauty, if you build your stuff inside Splunk and you use their fit and apply commands to build the models, you can then run a scheduled search and it retrains your model every time the scheduled search works. So if you want to retrain your model every week, boom, you put a scheduled search in there. It's really simple. And if you're a machine learning person, you don't quite understand this, we can show it. It's so easy to do. It's much easier than setting cron jobs and running a bunch of other stuff behind the scenes to keep your stuff retraining. So if you build it, you keep it in Splunk, they've got it really simple. And you can get alerted about your model and you publish your models. Nice that you build your model, it can be published anywhere you want. And the model just basically works for you. So anyway, and a model, the nice thing is when it builds the model, it doesn't need all that Python and all that other stuff there. All those dependencies, it doesn't matter because it built the model is a bunch of data. It's really a giant KV store, and it's not using all this Python code and dependencies. So it's really easy to publish else to other locations the model piece. Building the model needs to be done with, it's a lot more intense on the computer and you need a lot of processing and you need the dependencies from the Python libraries and all that stuff. But if you publish your model using Splunk, it's as simple as pushing an app out to someone and it'll just work there. So makes things really easy. Those are the general stages of machine learning. We've talked about what is machine learning, what are models, the fact that it is trying to make mathematical, statistical decisions off of data. There's predictive analytics and categories. There are anomalies and there's categorization. You've got, there's the phases of machine learning. You want to make a good story, you want to collect your data, you want to massage it, get it right, you want to experiment in it, you want to massage it, play with it, visualize it, then you want to build the model, deploy the model, reiterate through it. There's a process. This is pretty consistent across any place I've ever seen how machine learning does stuff. Anyway, so that's the general rule. Now that I've talked about this, we're going to move into the next stage, which is actually applying it. And I'm going to show a few different methods. The first thing I want to do is I take a tiered approach. And each of these tiers, in my book, there's, I want to use the term, do not let the quest for perfection be the enemy of good. And so there are quick, easy wins that you can do. If you build a model and it's really impressive, but it takes you 9 months to build that model, okay, but what if we could build five really good models using something not quite as pristine and all that, but it's still really good, and we can get five models done in that same amount of time? That's things to consider. So go for those quick wins. Everything doesn't have to be the most complex, complicated models. If it's easy and you get an easy win from it, do that. And so the first stage, can you get those results? Can you get your stories answered just using the Splunk programming language and statistics from Splunk? If you can, do it. The next stage, it's actually kind of almost first and second seem the same, but there is a slight difference, and I'll talk about that. Can you do it with SPL statistics and with a few KV, CSV lookups? If you can do that, do it. What about just using the MLTK as it rolls out from Splunk? If one of their algorithms works and it's good enough and it helps you and you can then just publish your model through that, and if you do it, then it speeds up the process. That's third stage. Fourth stage is, you know what? There are some new models, and yes, the MLTK can import models, but it's not quite ready to be this model. It's got to be dealt on its own. I need to be in the Python code on an everyday basis, tweaking and manipulating this stuff, and that's the fourth stage. All of these are perfectly valid, but as a general rule, I find that each of these grows in the amount of time it takes to create the models. And there is so much data, so much stuff to look for. We want to get as much things done. We want to get things done as quickly as possible. We want to be able to produce and provide value as quickly as possible. So I want to cover each of these stages. I'm not going to say one's better than the other, but again, if you can roll out and get good, good data that is usable by the analysts and doesn't create extra work, but answers the questions they're looking for with easier stuff, then do that. And ultimately make that your first solution and then ultimately roll out down the line. If all else fails, we can go to the other extreme and we can go download new and immersive models that are rolling out that are cutting edge, tip of the spear type models. Anyway, so now we're going to actually start showing these things in practice. And as I'm going to talk about this, we're going to do a little bit of a paradigm shift. I want to take the concept that there's the traditional IDS signature, and then there's the ML statistical anomaly. We've kind of stated what these are. An ML model anomaly, it's using math, it's using historical data to build these anomalies. So an IDS signature is a point in time alert. It's looking at network logs or host log, whatever, if it's a network intrusion or it's a host intrusion, whatever the case may be, it's going to look at these signatures and say, hey, I saw this set of IP addresses, I saw this type of traffic, and I saw this bits set of data coming in this order. That becomes an IDS signature. And those roll out, but the problem with IDS signatures is they hit differently in different environments. Different environments are different, and that is what makes ML statistical anomalies, that the ability to hunt there so much cooler, so much more powerful, is it's not static. If you can if you can get your data and you can look at it, then you can see what is normal in their environment and then identify the abnormal. And so what is abnormal in environment X may not be abnormal environment Y, but the beauty is you create that historical context, the way you search these will be different. Whereas IDS signatures, they are agnostic to the environment for all intents and purposes. You can do a little bit of tuning to the rules, but as a general thing, you deploy that rule, it is doesn't care. It's going to apply the same. It's going to judiciously judge the data the exact same way. ML statistical anomalies will allow your data to will be a little more flexible, and it will look at the environment and say this is normal. We're not going to flag that. Whereas, I mean, honestly, you could sit here and say IDS signatures, they're going to trigger on out of the box. They're going to trigger on scanners all the time. When scanners fire off, unless you block them out, they're going to fire. Your ML statistical anomalies will quickly recognize your scanners and should, if built right, they're going to accommodate for them, and without you having to do anything per se other than keep the normal upkeep of updating the model every week, boom, the statistical anomalies will account for the scanners. Anyway, so another thing to remember, anomalous behavior is not bad. It's possibly bad. All it really means when you're looking for these signatures, we're gonna do a lot of anomaly detection. I detected an anomaly. That does not mean there was a compromise. It just means I'm seeing something I've never seen before. You got to put your head, you got to put that frame on, and that's the way you need to resolve when you look at these. I am looking for something that I don't normally see. I've seen dashboards where people will track web traffic, and they'll look at the error codes. And all of a sudden, if there's a ton of error codes, bunch of 400 errors, there's a giant spike. That's anomalous. Does it mean it's bad? No. I mean, for all we know, it's normal operations, but it is anomalous, and that's what we're really looking at is anomalous behavior, not. And if it happens to be bad, that's what the analyst is doing. They're investigating to find out if it's bad. But we need to make that anomalous behavior as clear. What is the behavior that's anomalous? I need to be able to tell a story to an analyst when I show them this anomalous behavior and say, hey, what I saw was this IP, it did this kind of behavior, and it did it this, and then it did this, and then it did this, and it's never done that before. Are you concerned? You're the analyst. You look at that and you tell me, is that something we need to take action on? Or is that it was anomalous, but it was not bad? Anyway, so now let's get to some examples. All right, so the very first story, it's kind of a 2-for-1. We're going to look for abnormal ports being used in core light logs. This sounds really, really simple, and it really is. This may be way simpler than you're thinking for machine learning, but again, I want you to get back to one, I want to be able to give you machine learning models that I can demo in a short presentation in video format. So they are going to be on the relatively simplistic concept, but the framework is still the same. The concepts are still the same. And if you understand these quickly, you'll actually find you can take more complicated models and do the exact same thing with very little change to what I'm going to show here. So we're going to start with something very simple. And again, remember, it still fits the category of a model. We are going to use historical data to make predictions, to make decisions. And so we're going to define abnormal ports as ports that have not been used before. And we're going to do a window of, say, 90 days. I'm going to go abnormal ports over the last 90 days in my Corelight logs. All right. And then when I get done with that, I'm going to go look at abnormal tuple connections being used in Corelight logs. Tuples meaning source IP and destination IP. I just want to see, am I making new connections that I've never used before? All right. The other thing we're going to do then is I'm going to take you back to the tools of the trade. I'm going to go into more detail on these, but the first one, tier one, we're going to use Splunk. We're going to use some stats and some math. If that doesn't solve the problem, we can move to stats with lookup. If that doesn't work, we can move up to MLTK commands with anomaly detection. And this says tier 4 MLTK. Sorry, that's a misprint. That would be expanded models. I'm Here's the surprise. If I told you I was going to solve all these things, I'm probably not going to get to tier 4. All right, so let's kill this and let's go right to my Splunk instance. And here's my data. I've got index equals Corelight, source type equals Corelight con, and we can now look at the data. And I've done that by using this head command. I'm looking at these 100 fields. Remember, the first thing I want to do is, do I have the data? Well, yep, I've got connections, and I can see do I have ports? Yep, I've got it right there, id.response p, those are my ports, the des ports. Okay, so now I have the data. When I want to massage this data, you know what? I could, and so I'm going to. What are the fields that matter? I'm actually, in truth, if I want to get down to the simplest, quickest model, I just want to know anomalous ports. So I'm going to go table ID. Let's change this. I'm going to do it because I don't like this. ID.response H equal as dest port. Right there, I've now changed my field. Remember we talked about Splunk gives you the ability to massage and manipulate the data. This is simple. I'm just actually changing the name of the port, but I'm getting rid of some of the weird formatting. I'm putting in stuff that makes more sense. Dest port, that's the destination port, cool. And I'm just gonna go table dest port. If I did something like this, I grabbed 100, so I've really quickly subsetted. I grabbed 100, the first 100 records. I can actually now flip this to fast mode. Um, and basically what I'm getting here is I have reduced down my data set to the most minimal data set possible. And it would help if I put the right thing, response P as port. I got the response IP. So here are my ports. Cool. That now I need to go back to my model and apply statistics to it. What can Splunk do? Well, I love the stats command. This is like, as I like to say, stats is like Novocaine. Works every time, just got to give it time. Works every time. So if I go stats, count by desport. If I do that, it's going to go sum up all of these and say I saw these, and these. Well, I can tell you what's anomalous just in this 100 data set. 138 is relatively anomalous and 67. But this data set's way too small. So let's now open up the window and we'll just look in the last 24 hours. We can see, and I could write a sort command if I wanted to, or I can hit the sort button here. Again, that's the beauty of Splunk. It gives you some really easy abilities, but I'll just do sort on count. and everything that comes back with a value of 1, is that not the definition of anomalous? We could do a little change and we could say, no, I want anomalous to be 2 or fewer times. Cool. Okay. You decide what that number is, and that's the threshold you've set. But stats is going to come back and tell you that data. And so I can see everything. So if I say that anything that's occurred 2 or fewer times in a month is anomalous, well then that would be, I could just do something like this, where count is less than 3. And now I have all my anomalous data. So that's just anomalous. That's just, and in reality, maybe anomalous isn't the best term. It's not highly occurring, but it is anomalous in this data set. This data set that I've created, I've said it's not frequently occurring. Okay, cool. What if I want to do a different thing? What if I want to I want to look at the last 90 days worth of data and then look at today's data and tell me, did I go to any ports that I've never gone to before? This here just says, look over the last 24 hours and tell me I can flip this open. I can go. Let's take this to 90 days. Last 90 days, let that thing run. It's going to come back and tell me all the ports that I haven't been to, in the last 90 days that I've gone to very infrequently. That's really what this is telling me. And what a surprise, they're the arbitrarily high ports. Um, but that's something as an analyst I understand. Hopefully you understand what they are, what I'm meaning by that. And so there's some caveats. Maybe we want to exclude those and we don't want to count anything above, we don't want to count any of the ephemeral ports. Then you could actually come in here to your data and say des port, we could also go here, and des port is less than 1024. There, you get the exact number. Pick the port. It's got to be less than that, or whatever the case may be. You could go and eliminate that. Splunk gives you that capability. Looks like 90 days for the demo purposes here is going to take a little longer than I want, but it's fine. I was allowed to explain. I got 3 million events. I've done 3 million connections, and these 625 ports were considered to be, based off my criteria, to be rare. So anyway, let's then we're going to go, let's do something else. What if I wanted to find the concept and I want to look at each day, so I'm building an alert. I don't need to know, this is kind of FYI, these ports aren't used a lot. But what if I want to set up an active alert that says, look at today's logs and see if there are any ports that was a destination port that we haven't seen in the last 90 days. How would we do that? Well, now we need time. So I'm just going to add this time field. I'm going to keep this very simple. We're going to come back to doing a head 100. So I'm working with a very tiny sample of data. We run this. Now I've got time field. So I now know when this destination port was visited. Now we're going to go, so how do I find out, how do I set a baseline of what I've seen in the past? Well, really simple. I'm going to do stats earliest time as first seen time. And now, when you see this, it's going to come back, and this is going to tell me this port was the first time this was seen, first time it was seen, first time it was seen. Let's change this into human readable terms. So eval time equals, if I do something like this, the first time this was seen was today. These ports, first time they're seen, of course they're going to come out. They're all going to be seen today because I've made this subset that. I've only grabbed the first 100. Let's open this up to the last 30 days. Last 30 days, run this query. And now these ports are going to start changing their times. This was seen on 130. It's going to keep getting bit. Some of these you expect we're going to go back in time. 128. Notice as it keeps looking back in the logs, nope, I saw it at 127. And so it's building a baseline using time. And while this builds, so now what I want to do is I need to make Splunk recognize, hey, when this time is, if I see any events that the time is in the last 24 hours, that's anomalous, because realize it won't give me this if it's got an older date. This earliest command says, look at all the times on these logs, and give me the first time it was seen. So if it was seen today and it was seen a month ago, the date will be a month ago. If it was seen today and yesterday, the date will be yesterday. So what I now want to display to the user is anything where the time is less than 24 hours. So you're going to find what this time is, and if it's less than 24 hours old, then those are anomalous. So how do we do that? Well, what we're going to do is first we need to evaluate, we need to make this dynamic. So we're going to do current time equals now. This function gives me, so let's go and put these out here. I've now got an epoch. Oh, let's go back to doing 100 day, the head 100 again on this. Now I've got a current time, which is, it's going to take the epoch time. Tomorrow when I run it, it'll be the epoch time for tomorrow. So this number will keep changing every time this query runs. That's the beauty. I've made it dynamic. And so I can just set this as a scheduled task, and it's going to say, what's the current time now? And what I need is I now need to do another math, and I'm going to do um, eval. We're going to call this time limit. I don't know, which is equal to um, current time minus 86,400. If you don't know what that is, that's the amount of seconds in a day. So what I'm doing is I'm going grab the current time, subtract 86,400 seconds, and that's my time limit. My time limit, sure. All right, we'll throw that in. Now all of these fields have a time limit. What we could actually do, if you want to see this in really small terms, I could actually make this 30 seconds. So basically what I'm doing here is I said I wanted a day ago, but I'm going to run this on 100 logs. And basically what I'm going to do is now I'm going to see anything. I'm going to have these 100 logs coming back. When was the first time they were seen? And I've got a time of what was 30 seconds ago. And so I can do where current time, time limit, nope, where I don't want to use this time right here. We're going to comment this out because we need to use, it needs to stay in epoch time so you can do math on it. I miss a tick? Why aren't you coming back? Fine, we'll erase you. Should have commented the code, but it didn't. Okay, eval time limit, current time minus 30, where time limit is, current time is greater than time limit. If you understand time, time just keeps ticking up, so every second that goes by will be greater than the second before it. And what I'm saying here is where current time, this field, is greater than now minus 30 seconds, that would imply that this event was first seen in less than 30 seconds ago. I hope that's making sense to you. So I'm going to come back, and these are the events. And I can now flip this to put that back in, eval first seen time equals time. Oops, the other way around. Time equals, I just use this so it converts it for me. I could do a strict time, but I just like this. It makes it so much easier. This turns it to even equals. So I can see this thing was seen at 2331. That's probably not going to, it's going to be right there. It's a brand new alert, brand new. And so it's seeing these IPs, and these are brand new ports that weren't seen over the 30. And so the basic concept is it's brand new in the last 30 seconds. That's all it's really saying. And it's still a little misleading because I'm only grabbing head 100. Let's get this the real way now. I hope that makes sense. What I've done, I grab my con logs, I stats them, I grab the earliest time that that destination port was ever seen, and it's going to get written here. Then I'm going to grab the current time, subtract 86,400, which is 1 day. So I'm going to say grab the last, if this port shows up and the first time it was seen was in the last 24 hours, it is by definition a new port or anomalous. Okay, so now I've done this, I run it, and this number will probably reduce itself as we move up this chain. But we let that run. Well, that is silly on my part. First seen time, not current time. Where first seen time is greater, this field is greater than my time limit field. Silly rabbit. Okay, so all of these times had better be today. You by definition, because I'm throwing out everything that isn't, I won't see anything with a time here that isn't of January 31st. That's just going to be the way it works. And so here are my 50 anomalous ports, and that number may drop. Yep, it's going to keep dropping as it grabs more data. As it goes back more data, it's going to say, oh yeah, you know what? I actually saw them use that port. I saw them use that port. And there you go. I have created with a stats command, show me all new anomalous ports. Okay. What if I wanted to add a little complexity to it? You know what? Desk port's great, but I actually want to know um, the machine and the source port. Does that mean I want to know the destination IP and the desk port? I want to know that pairing. Oh, okay. What I do, stats count by dest port and dest IP. That quickly, I've changed the command, and now it's going to pair these two together. Oops, would help if I write them right. Dest IP, I need to do a rename here. ID.response H as dest IP. If I do that, now I'm searching by dest. It's going to pair things together by dest IP and port, and it's still going to do the exact same math. I run it. I should get more results. I only got 30 from the last one. I'm probably gonna get more results. And it's gonna take a little longer because I'm adding more dimensions. But it's actually still not gonna take that long. Interesting. Oh, yeah, I'm gonna take that out. This table here because that excluded the destination IP. And now if I run that, notice now I have dest IP to port. And when was it last seen? So this machine going to this port, that's anomalous. Not just the fact that I have port 443, but it's that this machine was the machine that was being accessed on port 443. And so I can run that very same query. I'm going to get those results. All these are going to be brand new. Oh, well, you know what? What I actually want, no. You got that wrong. You need more complicated stuff. We need more information. I need dest IP, source IP pairings. Oh, okay. So let's do ID dot org h, which as source IP, and I come in here and I go, cool. source IP. I just added a new one. Press enter. Now I'm doing anomalies on source to dest on dest port. I didn't change this. I told you this is my, it's just like Novocaine. Give it time, works every time. I, I can put as many dimensions as I want in there. Wait, but didn't you tell me that machine learning needs to, in order to do anomaly, you need to normalize your data and get it into statistical values? Yes, if you want to use the Python machine learning, but if you want to use Splunk and statistics, I don't care. It can handle strings because it's not using statistical software in the same way that is limited to only using statistics. You must pass in statistical values. I'm not trying to cause problems and upsetness, but the fact is it handles strings just fine. As you can see, this is a string, this is a string, this is an integer, doesn't care. It doesn't matter how many of these I have. It'll just keep doing it. It doesn't throw a fit because I have 100,000 different source IPs, destination IPs, etc. It's fine. Doesn't care. Um, here's something crazy for you. A lot of the time you need in Splunk and Python, you've got to come up with, when you're using those Python models, you've got to come up with a way of converting the IP and the dest IP. And well, the problem is then they become numbers. And how do you keep these pairings together? I'm going to give you a weird one. What if I want to do this? Eval foo equals source IP plus pipe plus close plus dest IP. And now I have made a new value. This is saying make a field and make it source IP separated by a pipe and a dest IP. And I'm going to actually close this out. And I'm going to put, instead of doing source IP and destination IP, which is a 3-tuple system, I now flipped it back to a 2-tuple system. So the very same encoding you do, one of the ways you could encode with your Python, I made it even easier. This is still a string, but look, I can pass this right back. I'm actually going to get speed improvement because I reduced down the tuples, yet I still have the cardinality, the ability to make this distinct from everything else that you would really want of having a source and a destination. But I now have one string value I'm comparing, so I've increased performance and it's simpler. I'm just going to point this out. This seems like a massive win. I'm also looking over 30 days worth of data. Really not too bad. Okay, now, wait a minute. But I thought you had a whole tiered approach. You said that you could do stats, and if you didn't work that, you could do another. All right, let me tell you the use case where you might want to move. I've got a use case I can't solve with this simple command. What if I am not looking at my alerts and I get in an anomalous IP address, say this one right here? Won't that mean that tomorrow this is part of my baseline? So tomorrow this won't be anomalous. And now the alert person, the person's not going to know those getting, I won't be creating a new alert on that. That that doesn't work for me. I can't, I've got to have a little longer period of not retraining my model. This technically is training the model right there on the fly. And so every day you search it, tomorrow this field won't be anomalous anymore. Oh, okay, cool. Well, let me show you how you solve that. Oops. If I go back to my Splunk here, stats with lookup. What does he mean by that? All right, I got 67 values here. And what I'm going to do is I'm going to go the other way where first seen time is not less than time limit. So I'm going to grab all the things that are new, but I could actually do something like this. Um, so I don't actually, I can take this whole current time out. And what I'm going to do is I'm going to build my baseline of values that are part of my baseline like this. And all I do, so nothing changed here. I mean, this is just give me all my tuples, dest ports, first seen. This doesn't take time into effect. This is my baseline of acceptables. Anything that's not in there is anomalous. Cool. Now I'm going to do output lookup anomalous ports.csv. What this is going to do is it's going to write these results into a CSV file. And we'll open up a new tab when this thing's done. Probably should have, let's take it down to, we'll let it run the 30 days. The concept here is now I've made a lookup. And now when I run my alert, I'm going to grab 24 hours worth of data and I'm going to join this data on the new data. And anything that pairs up and doesn't match here, that's my anomalous data. And the beauty is until you re-output the lookup, today it's anomalous, tomorrow it'll be anomalous, the day after it'll be anomalous. So if you need your stuff to be anomalous and you need to keep that data, you don't want to refresh your data model every day, go use lookups. So we've used stats and stats with lookup, and we've been able to do anomalous here. So I'm going to come and grab, come on, finish up. So I've got a little lookup here. We're now going to duplicate this tab. And how do we look at this value? We're just going to grab pipe, input, lookup. There's my ports. There's my list. Here's my key right there. And so what I'm going to do, I'm going to go grab, this is how you do a lookup. We got to grab the data we want. Index equals corelight. Source type equals corelight con. And now I'm going to do is lookup command, look up anomalous ports. I need to actually make that foo field again. Foo is a horrible term. We'll need these. So we're basically renaming the fields so they match. I make my foo, and you don't need foo as foo, but this is the concept. When you make a lookup, you say, what field are you matching? If you don't, it'll look and say, do I have a field in here that I have a field over there? And yeah, foo. But I don't want it to match on desport. That's just something I want to avoid. So I'm going to call it out and say foo as foo. So foo from this lookup and foo from this data. And then I'm going to output, let's just output the count. It doesn't really matter what I output. Oops, I don't need the last 30 days. Now I'm going to go grab the last 24 hours. And I'll just do a table. Foo and count. Anything that has the count field, it matched. Anything that doesn't have the count did not match. And so if we come down and we go, so what I really want to go to is where is null count. Run that command. I'm not going to have any anomalous because my query grabbed the last 30 days. Everything's included inside of it. But this command tomorrow will catch all new anomalous behavior. All I've done is it's the same command, but I just don't have to do I don't have to do any of the time pieces. And I make a lookup, and then I apply the lookup. And when the lookup matches, it's not anomalous. When it doesn't match, it won't output anything. That means the value will be null, and that's what I want to see. And I do that, bada bing, bada bang, I have my model. All right, well, let's look at this. Is there any reason then I should go to anomaly detection? Well, I'm going to tell you, I already solved the problem. But let's go back to something simple. Index equals corelight. Source type equals corelight con. This is going to cause controversy, I know it, and I'm sorry, but it is what it is. I'm going to do, I want to rename those fields. I just like renaming them. You can do this without renaming these fields. So let's not for this point, for the sake of this. Stats count by ID.response P. I've already done this query for you, but I'm just looking at the last 24 hours. Give me all the ID.response. Why? Fine, we'll read it. What did I do wrong? ID response. Oh, it doesn't like the periods. That's why I get rid of them. That's why I do it, because you don't want to have to deal with those periods. I forgot about that. That's why I always do it. Oh, go away, reading list. Cool, I don't know why the reading list has popped up. Go away. Okay, now if I do this by desk port, what is this wrong? Index. Well, it would help if I wrote this right. Okay, maybe I could have done the count. I probably could have done the count either way. All right, so now I've got, we run this count. All of these ones, they're anomalous, right? That's the definition of anomalous. Recognize something. These models that I'm going to use from the MLTK, they are not actually Splunk models. All really that Splunk has done is it's created a wrapper. It grabs the Python commands and puts them into a Splunk syntax so that you can call them from Splunk. So I can do anomaly detection. There is an anomaly detection algorithm in those Python libraries. And the principle is we just put in what fields we want them to detect as anomalous, and we can run that. I should have done that on 2 different pages. Okay, so that's running. This is running stats count by. Basically the same data set. I need to put a table here so you can see it. Table dest IP. Dest port, so you'll see the results. And it's going to call out what it thinks are the anomalous ports. It finds 27 ports it thinks are anomalous. And they're all going to be the exact same percentage because what it does is it looks at the entire collection of desk ports and says how many times did I see a frequency analysis desk port. I could do the same math over here if I wanted to, but I just want to point something out. If I go count 1, I've got 20 items to a page, so there's 20 here, 40, 48, 50, 50 something. 50 something ports that are by 1. How many did the anomaly detection detect? 27. I'm going to tell you, I don't get it. Why is this one anomalous, 53792? And that's going to be found over here, 53792. If I went back 1 page, it'll be on that list, 53792. Yep, it occurred once, but the other ones aren't. I'm going to tell you that I'm not 100% sure I like this. It added some complication into it. I don't know that I agree with the numbers. I'm not sure why it did that. I mean, I wonder if I ran it in pure Python, if there was something, I don't know what happened. There's some glitches, but I also know that this command ran faster. If I look at the time that this command took to run, I inspect it, it actually takes less time, 5.4 seconds. Watch the minute I say it won't be faster, but as a general rule, I'm glad. Okay, this was almost a second longer. The bigger the data set, the longer it takes. Why is it longer? Because it's got to go run the Python, it's got to do all that stuff, it's got to do the conversions, things like that. This is just native Splunk. So is that a reason to not use the anomalies and other things? No, no, no. Just, you know what? I don't need to move up the model. I could if I want to, if I find that I'm going to get better data, but I'm not 100% sure I'm even going to get better data. And the fact is, you could run a ton of things and say, tell me what's anomalous. But I'm going to tell you that my eyes will tell you that what I was doing with those stats commands earlier, that's anomalous. I don't need another model. I don't need some fancy schmancy model and with all these different variables and things to basically tell me it's anomalous because I know it's anomalous. I've never seen it before. Now I have. You could put how anomalous is it? Well, you know what? I can do the exact same thing with Splunk because I can do math over there. I'm not going to do it here. There'll be some other examples as we move on where I will be demoing the uh, more math in there, and you can see I can do the same thing with math just straight in here and not even waste my time with all the different models. One time I'll put all the models together. That'll probably be my very last example. And honestly, when you look at them all, if the simple model provides the same value and it actually reports back the same way the analyst would call it anomalous, that's probably the easiest thing. I wish I had the name of the professor, but there was a presentation done by an MIT professor. He did not, he got flamed bad by the ML community, but he flat out said, you know what? More often than not, the simplest model is actually the best model for machine learning. The more complicated the model is, he says, I have found that over time they are less reliable. You know what? The guy had a lot of credibility, he said it. I'm just going to tell you, I don't want to get that art, but if it's simple and it works, just use it. I was able to create a model to detect anomalous behavior on ports, on tuples, just that fast. It took me minutes. This presentation's like 30 minutes. I don't know how long this section is, but it went really fast. We're gonna do it again, and we're gonna do more complicated models. And sadly enough, they're probably gonna take less time because I'm not gonna spend as much time explaining what I'm doing. If you can put out a model that does that in 30 minutes, why, and it meets all your criteria, why wouldn't you do it? Anyway, so I guess it's time to move on to model number two. All right, let's discuss another story. And this story, we're going to look at anomalous detections in network connection log history by IP tuples. The concept is we have our con logs, it's keeping track of a history there. And our theory is, and it could be right, it could be wrong. Again, we're trying to keep these simple. Our idea is that there will be generally the same type of history between these IPs, and particularly internal, because we don't want to talk about what's going on with the internet or the internet talking to us. We want to just say that our network, our little subnets are relatively static, what they do, that communication inside each other. So we would expect that generally the history will be the same. But if all of a sudden a different type of history occurs, that might be indicative of new anomalous behavior. So let's go and put that into action. We're going to breeze through this, but we're going to come back tools of the trade. First, can we do this with stats and math? Can we do it with stats and lookup? So we'll start. So can we do this with tier one? All right. What we're going to do is we're going to come in here. I'm going to write me a query. Index equals correlate. Source type equals correlate con. Going to grab the first 100 fields. What do we get? We can see, oh, we got a history field. That's the field I'm looking at. There are different histories. And I could go look those up if you really want to find out what they mean, but I'm actually going to use this concept. The beauty of this is if someone's giving you a good story, you don't have to know all the other details. I'm just going to look for what's I'm just going to look for here for some anomalies. Eventually, when we start to go through and refine the model, it might be helpful to know what every one of these categories mean. I do know that uppercase is like output, lowercase is input. It's kind of the direction the data is coming from. But ultimately, I'm just looking at these different history fields and trying to say what's normal and what's not. Well, first off, let's go and just check, is there a bunch of anomalous stuff? Stats count by history. If I run that, I can see that this occurs a lot. This is almost always guaranteed. This is UDP traffic. Oh, what do you know? It's a little odd. Um, and so we definitely have some anomalous. And yet we have some data that is relatively consistent. This might be a decent data set here. All right. The other thing we want to do is I didn't want to care about, I'm not looking at internet connections. I want to just be paying attention to what's inside our network. So I'm going to do id dot org h equals. So what I've done here is I've said I want all the responses and the origins, the source and the destinations to be 192.168. That's my internal subnet. So if I run that, I'm going to throw out a whole bunch of these connections and shrink down my data set to something a little smaller. And now look at that anomalous behavior. Still got a lot of that, still got a lot of things that are pretty consistent. And then we can see that they start to peter out. Interesting enough, I don't have any ones. That's kind of interesting to me that there are no just a single occurrence of a history. There's at least two of them always. Hmm. Okay, so let's go write this command. Just so we get this going the right direction, let's go head 100 so I don't spend a lot of time as I rewrite this and mess up my stuff. We're going to do a stats count by history. What we want to do is earliest time as first seen time. By history, we'll start just with history there. And we should start seeing times here. Yep. All right. We're going to do an eval now. Current time equals now. So now I've got my time, and then I'm going to go eval time limit equals current time minus, once again, we're going to look at the last day's worth of traffic. So we'll go minus 86,400, where first seen time is greater than time limit. Let's open this up to say 7 days. Run that query. Can't do a head 100, that won't work. Otherwise, we don't have any historical context. So I had 26 new connections, new histories that I hadn't had over the last little bit. All right, that's interesting. Let's now turn this into nice human readable. Time eval time equals. Make sure we're happy with what that time comes back. I bet if we open this up to say 30 days, we're going to find, we will not get larger. If we had 26, you open up your window larger to a larger baseline, the number will only shrink. It's not going to get larger. If I were to shrink this to say, look at the last 5 days, the number could get bigger. But the longer the data set you make, the time you look back, the less anomalies you're going to have. That's just the way it works because you got a bigger baseline, more data to draw from. All right, well, number's definitely down. You know, out of a 17 million events to find 12 anomalous, that's not a lot. It's still more than I probably want to be looking at, but I do think it's interesting. They all fit as 2. I don't know what that means. That's something definitely worth investigating. Why is it 2? Why specifically 2 of these? Um, anyway, That works. But now I don't care about just about history. Let's do it by source and destination IP. So if I do this, I get a lot more results, but I'm also going to get a little more context. Well, I don't know, I'm going to get a lot more results. But again, as you can see, it's just easy as adding those tuples in there, just adding the different more values, and now I'm doing the exact same query. I hope you're getting this concept that with this conceptual concept here, I can pretty much do this against any form of data type and start to see kind of what is the baseline and then what deviates from it. So it looks like the data is relatively the same as what we got from the other result, other than we're now getting these little UDP ones. They weren't abnormal because UDP occurs all the time, but this machine had not been talking to my router UDP, and it had not been talking to this machine UDP, and now it is. So that's the abnormal. So we can see really quickly that we have managed to, just with stats and math, we've managed to make it work. We could do a lookup and attach the lookup on there. But again, that model just continues to work for us. All right, then let's go to another model. We're going to take it a little more. This time we're going to use some historical data. I'm going to push us to the bots data, boss of the sock, and really go into stuff that we don't really, may not know anything about. I really don't. I'm just going to go look through them and build some anomaly detections off of it. Okay, we're going to give one more example using almost the exact same methodology, but this time we're going to use the boss of the sock data. You can download that from just Google bots v2 download, and you'll find a Git repo, and you can pull it yourself and do the exact same thing. But the point is, I just want to show I can do this with any set of data. Again, I'm going to do host logs. Here's my story. I want to find anomalous login activity. And I'm going to define anomalous login activity as in machine people logging into Linux boxes that don't normally log into them. So let's find new users or from new locations. And let's see if we can find any logs that will help us on that path. If I jump over to the boss of the sock data and I look at the source types, I'm going to come down here and I'm actually going to see the, so back here, here's who, the who log. Well, what's in the who log? The who command is a command that tells you who is currently logged into a Linux device. So if I go index equals bots v3, v2, source type equals bots, nope, equals who, do a head 100 so we can investigate this data. This data is very historical, so I'm going to use it all time. Not a recommended approach, but it's a set. I know the set of data. It's okay. I'm going to pull it. What I see here is host name. That's where you came in from. Host, that's what the machine you're logging into. And username, that's the username that was logging in. So let's go look at that data. Let's try the very thing I've been doing this whole time. Stats count stats earliest time as first seen time by host, host name, is host name right? Host name and username. Run that command. Boom, got it. Okay, now I jumped here and I wanted to see the date. My data stops coming in on the 8/29, 2017. You know what? So I'm going to go look historically. I'm going to go to epoch time converter. There it is. And so if I put in a date, and so we're looking at, I want to use 8/28. So 8/28, 2017. Month 8/28, 2017. 17? Short memory. 8/28, 2017. Cool. And we'll put this at, sure, whatever. There's my epoch time. I'll just copy that out. And now I'm going to do eval time limit equals, there's my epoch time. I don't need to do any math. I don't need to do now because I'm not looking at now. And I'm going to do a where first seen time is greater than time limit. And let's convert eval first seen time so it's a nice human readable. And that's going to fail. Okay, doing that. What I end up finding is this user logged in from that machine, sorry, from the console to here, and they've never done that before. This is a really quick way. I've now got the ability to lock, see who's logging in. General rule, especially on servers, you're going to have certain individuals log in from certain locations. If that changes, this will flag an alert. Just quickly baseline the entire who system. All right, this is all good and dandy. Now we're going to take another step forward, but that's going to be using some math because sometimes it's not about did it occur, did it not occur. It's did it occur way too much? Did it occur outside the norm? Like, for example, error logs on a web server. If, what is the average number of errors that occur? How many 400 errors am I getting? Did it all of a sudden jump from above the average? The fact that it occurred is not the anomalous behavior. It's the fact that it occurred so much more than it used to. Oh, well, that must mean I need a complicated model, right? That's now we found the reason why you need these complicated models. Well, let's go see if we need a complicated model or not. All right, I've got another scenario going on, and this one is we're going to use math to improve our SPL. I told you that we had, in our last one, we had some deficiencies. What if we want to, we can say, yes, an event occurred or no, it didn't. But what if we want, here's an example, we have web servers. Web server request, and you get a status code back. And getting a 200 code is not anomalous, that's a normal thing. But what if all of a sudden you get a massive spike of 200 codes? Or what if you get a massive spike of 400 codes? Or all of a sudden you're getting very few 200 codes? That might be an anomaly. It's not about whether it's not the Boolean concept, it either happened or it didn't. It's based off of a percentage. You need to be looking at the data. And so what we can use Splunk to create a moving window to check what is the median value, figure out the standard deviation, and make an upper and lower bound, and find out if the data fits in there. I'm not going to go through all the math as I write the code because the chance that I screwed up is very high. What I did is I took the bots v2 data set, grabbed the web logs, and what I did is I said, let's break this stuff up into 10-minute buckets. So I made a bin on the time field, and I say span it 10 minutes. And then I ran a stats command. I'll keep these results here. I'll come over to this one here, and I'll show you what's going on. As we do this, I run the stats command. Should be familiar with this concept. Oh, let's go grab just 100 of them now. Head 1000. What it's going to do is it's going to go grab time chunks, break them up into 10-minute chunks, and we're going to get the number, the dest IP, the status code, and how many it saw. Next, next 10-minute chunk, how many it saw, how many it saw. And so it's just going to have that nice little window rolling there. Then we use stream stats. Stream stats allows us to keep all the values. This is not a class about stats versus stream stats and all that, but the basic concept is we have a rolling window. We then get the median count as median by dest IP. So we're basically determining what's the median value of count, what's the median value in that 10-minute chunk. Tell me what the median was. And it will store that median. Cool. Now that I do that, I can do an eval, the absolute value, get the absolute value of count minus the median. That way it doesn't matter. We want absolute. That way we can get positive or negative. It doesn't matter. Then we go and determine the stream stats and we get the median absolute deviation. Same principle. We do a lower bound, which is the median minus the median absolute value times exact times 20. So you're just basically, you can use whatever math you want. I shouldn't say that, but we're establishing our lower bounds and our upper bounds. I'm choosing to use median plus median absolute times exact 20. I don't have to do that. I could do an absolute value function. I could do standard deviation functions. Those are all supported natively in Splunk. I mean, you want to see standard deviation, it's as simple as standard deviation. There you go. You can get the standard deviation value, then you could apply it. Um, anyway, get a lower bound and upper bound, and you basically say, is it an outlier if the value you were looking at count, or this count here, is less than the lower bound or the count is greater than the upper bound. And so we get outliers and we can see this, that this value 22, with your upper bound was 112 and your lower bound was 32. So it fell outside that bound and thereby it was an outlier. And you can go down and you can see how each one of those and the other ones are not outliers. I don't know how many outliers we have. If you restrict down that outliers, you could probably really cut down on how many values come back, but there's about 45 out of all these events. And basically we can see that 172.31.72 with the status code of 200 had a spike. Did we get any status codes? I have no idea. If we look at outlier, let's go back to our outliers. Were there any standard deviation? Not 200. Well, knowing that, and if in our environment oh, we got a 304. That, my friend, is an indicator that I would be very interested in, because maybe they've got the way they've got their web server set that a 304 and these 302s are basically 400 errors. Remember that they can sometimes redirect, and these might be examples of a machine getting pegged incorrectly. This would be, it's not a ton, I guess the count, they just actually just barely showed. The fact that they showed up means they don't show, they actually show up. Normally they get a lot more 300 errors. Interesting. Okay, so I'd reassess that statement because they're on the lower end and it's 300, probably not concerned. So you could actually do some logic here where you throw out, I don't care about status codes of 200. You might say here, if it's a 200 code and it goes low, I care, but I don't care if it goes upper bound. If it's a 400, so you could do like count and count. Oops, I can do this. I can do this. Come on. I've lost my ability to write in here. Count is less than. Cool. It's not going to let me write. For some reason, I can't write in here. I've lost my ability, but I could write count is less than and status code is greater than 400, then do this. Anyway, so it gives me a lot of different capabilities to massage and manipulate, but this continues to constantly look at the previous data and say, what were those bounds? And so I can build a model really, really quick Again, just using math. Now, to be fair, all models are based off math, but the math can be done natively in Splunk, and it can be done really quickly. So anyway, that's another example. We'll continue to show more examples. All right, we got another example, and this one is just solely based on math. My examples are just getting worse and worse, I'm not gonna lie. This one here is I wanna see in my logs if there are the log flows, if there are spikes or lulls in the logs. So we're gonna look at time and say, hey, what is the normal amount of logs coming through? And are those spiking or are they going down? Um, and we want to use this Poisson distribution, which the concept of the Poisson, I can't do this right now. Poisson is, it uses a fancy math to basically predict based off previous values whether or not these values should exist inside the data set. That, I think that's how that works. Details aren't that important. It's the point is that this is the distribution I want. I know how it works. So let's see if I can make Splunk do it. Well, I'm going to comment out each of these lines as we go through them and walk you through what we're doing. So if I come down here, first thing we do, we're just going to go grab tstats. It's a fast command. Go look at the last 90 days and tell me every 10 minutes how many logs was I receiving. It's got 65 from con, DNS, et cetera, et cetera. So I can see how many files are coming through. So how many logs. All right, so now I've got my data set. I quickly created a data set. Now I want to create a key. And in order to do that, I want to figure out what the hour of the day is. I'm going to pull that hour of the day out and the day of the week. So if I pull this off, put that down here, we'll now get an hour of the day and the week. So Sunday at 7, Sunday at 7. That's all we're doing. Now I'm gonna make that a key by using the term make key. I'm gonna make the key source type underscore hour of day underscore day of week. Now I have a unique value. So I can now, using this, I can use this key that I can basically say I can compare all Sunday at 7 o'clock. Was one Sunday at 7 o'clock versus another Sunday at 7 o'clock. And I get an idea of how the data compares at similar times. I just built myself an easy, simple key. No issue. Pretty simple there. This has lots of different applications, but now I got a key. I can use it, and it doesn't care about this time. Now this time can be ignored, and I can use this to compare similar values. Now I'm going to use the event stats. What I want to do is I want to find out what the percent 95, that says, hey, give me the 95th percentile. Find out how many logs come across and tell me what number would 95% of the logs would qualify for it. And I'm going to put that as my upper bounds by source type. I could put a lower bounds if I wanted to. This one here is just going to be looking for spikes then. And so I'll take that out, put this in, and what we end up getting is it's looking at that source type, and we can see what the percent 95 is. 1633 for correlate cons. Typically, that's what I'm receiving. This is definitely not a normal. Um, and so you can just see basically that concept. We then are going to go say, hey, where the count is greater than upper. Basically, I want to remove any of these anomalies where it's a drop because that'll mess up my numbers. I want to know where there were spikes. So I'm going to remove all these smaller numbers. And so I'm going to do that stat where that's greater than. I'll move to the next step. Then I'm going to count and I'm going to make the word cardinality. Those who are familiar with statistics, that's the unique values, how many times it appears, there's a few different ways of saying it, but basically count. I'm going to call it cardinality. And I'm going to give the average count as the average by the key. Now I'm using that key field to compare them together. And I'm basically going to look at what the average is. And then I'm going to export that result into, let's call this Corelight event count averages. And so I'm going to just print the results right into this CSV for the last 90 days. Let that chug away. It's not going to take that long. This is building my model. I just built a model with Splunk, and I can basically say, hey, on Corelight Cons at 0 o'clock on Sunday, uh, at least 6 times I saw things have 3,923 logs on average. That's what that's basically saying. We can see that Friday we really struggle. There's logs all up and down the on Friday at 7 and Sunday at 7. It's all up and down. So there wasn't a lot of consistent data there. This was pretty consistent. The higher the cardinality, the more you can trust that those numbers are consistent. And of course, you'll get higher cardinality the larger the more you move your data set out. Because, well, for example, if I did 7 days, I could never get more than one cardinality because I'm never going to cross Sunday at 0 o'clock midnight is never going to occur more than once. And so part of this is it can only occur so many times to begin with. And then it's got to match those percentages. And I'll tell you that if this isn't really close to how many, like 90 days, that would be how many weeks? 70, so 10 weeks, 14, 13 weeks, 12, almost 13 weeks. You're going to want to see a cardinality maybe a little higher. Otherwise, you can see that the logs are jumping all over the place. This is probably my most consistent log then, the SSL on Wednesday. Um, Without high cardinality that matches how many occurrences, me personally, I'm going to say this data set's probably not very good for this model, but we're going to follow through with it anyway, even though the data is telling me don't do it. I don't match up well. But you know what? I never listened. So we're going to come over here and write a different query. It's pretty much the exact same thing. The difference is we'll start right here. We'll cut this off. If we notice, everything we did up to this point, the first 3 lines, they're the same. First 3 lines, first 3 lines. So we're grabbing the same data, but now we would go grab, say, the last 24 hours. Or we go grab the last week, whatever, because we can do a week. That's totally okay. We don't have to run this every day. And then we run this lookup file. And basically what it's going to be doing is it's going to match on the keys and it's going to give me the average and the cardinality that it expects for those values. So if I put this in there, we grab the last 24 hours, the lookup command. Well, it would help if it was called correlate. It's got to match the name on the other one. Correlate, event count. Now we have the average and the cardinality when they matched. Looks like we have some files coming through on Wednesday, and we've never had that before. That's actually kind of interesting that we didn't have those logs. But it is what it is. Surprised that there were no files. I guess not having files in DNS and con, that's not the weirdest thing in the world. Um, but so we can see the match, and now what we're looking for is we want a cardinality greater than 10. I'm going to go cardinality greater than 5 because we don't have very good cardinality. And so I want to exclude anything that might be basically, I'm looking at that cardinality over here and saying, you know what? I only care if I don't have a high confidence over here, don't get rid of it. Throw that data out. We won't call that anomalous. And so I'm going to go where cardinality is greater than 5. And now we're going to build our little Poisson model. Oh, I got nothing matching, so we'll have to go greater than 2. Really bad cardinality, but whatever. So I got a bunch of 4s. All right, cool. Now we're going to use our Poisson method, and I'm not going to walk through the whole math, but we're going to get factorials. It's the square root of 2 times pi times the count times, I'm not exactly sure what POW, power, the power function of count divided by the exponential of 1, count exponential equals exponential average. You know what? I didn't write this, I stole it. But all the features you need to write that query are right there. And write that math. Then you do a probability of power, average, blah, blah, blah. And then basically you do an outlier. If the probability is less than 0.03, I can modify that. I can say I want my threshold to be 0.01. And basically then I will give myself outliers. You take these tick marks off, and I can see the data that's outliers in the last 24 hours. And I don't have any. I'm not actually that surprised. Just didn't have enough data to make it work. But let's just put that in there. I'm actually kind of interested that there's nothing about outliers here. All right, we'll open this up, open the floodgates, go the last 7 days. And anyway, if I had the outliers, they would show up. And, but that's just an example. Again, I can just pump in the math right here and I can see the values. I don't have, we'll take the probability and go back to 3. I don't think I'm going to get anything either way. Less than 0.3. I'm not going to get anything. But again, you can put complicated math in there. You can run the functions. Um, you'll just have to imagine that the outliers actually popped. They didn't, but they should if there was actually outliers that it was detecting there. Um, yeah, I just want to see this. What's going on? Really weirded out by the fact I'm not getting all those fields. Let's just do it by source type equals correlate con. I want to be able to look across all those different fields, but that's still weird, those Fridays. Anyway, so now I got my cons. Now if I do this, there's something weird. We didn't match anything. Okay, let's just not eliminate anything here. Do do do. Okay, a lot more values. 0. Okay, now we come back here, run this. Okay, we're matching. That's a lot better. By the way, if you notice, it's 2:41 in the morning. I am clearly tired. So why? It's going to throw you out. All those cardinalities should have matched anyway. Oh, sheesh. I'm retarded. This is working. Okay. So if it's less than 0.3, it's a 1. If it's a point, if it's not, it's a 0. So none of these fell. I could try to move this out a little further, see if I get any ones. What I want to see then is just do me a solid here and just give me the anyway. I wonder if I don't remember which way I need to go. Do I need to keep extending out the zeros or go the other way? Well, I got to figure out exactly where the math is off, but the concept is I get all the way down to the probability. See if I flip this to 9. That's funny. I get a different value. So there must be a copy paste error from when I did this example. I'm I don't want to go any further on this. Not my best example, but I just wanted to give the concept here that you can do math right there in your stuff. And it didn't take that long to build this function. Again, if you want to use the Poisson method, all you need to do now is come over here, build your key, come over here, apply the key, and you're done. All right, I have given lots and lots of examples, and I've never actually used any actual models out of what is typically considered models. So our next example, we will actually show using a model inside Splunk, MLTK.